this is going to be a pretty similar example to what I showed you before, right? But this time now you're scanning over molecules or line diagrams of molecules, and it's giving you a ball and stick diagram of the molecule in return. Right, so it has to do the same thing, right? It has to recognize the pattern in order to draw you the molecule. You can even do this for a cup of coffee. So it recognizes that it's a cup of coffee, and then of course it goes through the molecule caffeine. Yeah. So yeah, the applications of machine learning are rapidly expanding, right? I showed you a couple examples in classification, right? One of the more traditional uses of classification might be for determining images on Street View. So for example, you might wonder if you're trying to automatically label maps, you might look at this picture and try to figure out that it's a gas station. It's also been used for generating images. So here's an example of a wacky picture that's been generated by a machine learning model, but it can also be used to generate text and generate images. And it's also been used for natural language processing, right? So for any sort of recommendations lookup, it might use the natural language models to do this. But today I'm going to be discussing with you two applications of machine learning to chemistry, in particular in the field of chemical sensing. So now let me get into what do I mean by chemical sensing, at least for the purposes of this talk. So we're thinking about identifying sources of chemical traces around us. And this happens in a lot of different domains, right? This will happen when you're using spectroscopy. You know, this is another form of spectroscopy, right? Used at an airport to determine the contents of beverages. This also happens when you're smelling objects, right? Like when we're smelling something, we're doing nothing more than smelling the chemical traces released by the flower or the cup of tea or the sources, whatever the source of the smell is. This is also relevant for insect repellency, right? Because in a lot of cases, insect repellency is about trying to find compounds that mosquitoes or insects do not like and therefore will stay away from and then therefore leave us alone. Here's another more specific example of chemical sensing. This is the story of Joy Milne, who was able to detect her husband's Parkinson's disease at a really early stage just by recognizing that one day he smelled different. So one day she just noticed that he smelled different and they couldn't figure out why. And it was only years later that they realized that he had Parkinson's, that they were able to attribute that smell to disease. And when they had, when this lab in Israel did this test on, with her on a bunch of other Parkinson's patients, where they gave her 10 different subjects and the smell from 10 different subjects and asked her to identify which ones had Parkinson's and which ones did not. She was actually able to identify them 100% of the time. Now, you might have also heard that dogs are capable of the same thing too, right? Like dogs have also been known to be able to smell the breath of patients and determine who has lung cancer. So the next step that they took, this lab took, is that they used this technique called GCO, so gas chromatography olfactometry, to try to identify which metabolites were responsible for the smells that Joy was picking up, and then use mass spec to determine what are these compounds. So this is a really cool area of research, and I think one of the promising avenues for chemical sensing. Right, so the goal of my team then is to digitize chemical sensing. We're working towards developing an electronic nose, but more generally, we're working towards developing a representation of odor. So what are the implications? You can think about this, right? So we can have faster determination of unknown samples, right? If we are able to if you're able to predict the molecule directly from the spectra or expand our libraries of spectra given a molecule, that could mean that we could have better coverage and better identification of molecules. We can do this for scent, right? So if you think about it, we can take pictures or take recordings and send them to other people, or even have a Zoom call like this, because we have an RGB for vision, right? Like, and we have a encoding for sound, right? So basically, right, my camera is encoding the image that it sees right now of me, and then transmitting it to you. And during the process, the image that it sees is being encoded into this RGB coding, right? We can't do this for smell, in part because we do not have an RGB for smell. We do not have this notion of a representation for smell. But what if we did? If we did, you can imagine doing so many more things, right? You could imagine, you could take a recording, a scent recording of your favorite dish, or maybe some food that you tried on a vacation or a trip to another city or something. And you could play that recording of that food back. Or you can imagine, like, you're watching a cooking show, you could even imagine having the smells of the food being transmitted to you while you're watching the cooking show. So I think there's really unlimited possibilities if we really develop this, not only like the representation of scent, but also a device to play back the scent. And finally, as I was talking about with the story of Joy Milne, right, if we could somehow capture what it is that she is smelling, and turn that into, and make a device that can detect the same volatile organic compounds that were the metabolomic indicators of disease, you could imagine that we would have a very cheap and non-invasive medical diagnostic tool that would be based on breath. And if you could put this on phones even, then this could be a test that anyone could run on their phones. Right, so the two parts of my talk today are two steps that I see as very, very early steps towards this goal of creating digital sensing and creating an RGB for smell. Right, so the first part of my talk will be some research that I did during my PhD while I was an intern at Google. And it will be on expanding compound mass spectral libraries using machine learning. The second part of my talk will discuss discovering a representation for scent using machine learning. Okay, with that, I will get into the first part of my talk. Right, I worked on this project with David Bellinger, Ryan Adams, and Dee Scully. And I think most people here are probably familiar with mass spectrometry, so I'll go pretty quickly through it. But right, in general, you have an unknown sample, you ionize it using an electron beam, you accelerate it through the magnetic field, and then the detector picks up the ionic fragments, and basically your resulting spectrum looks like this, where you've got mass to charge ratio of ion fragments on the x-axis and the frequency of the peaks on the y-axis. Now you can reverse engineer what the molecule must have been based on the frequency of the peaks and locations of the peaks. But another common way of determining what this compound is based on the spectrum is to look it up in a mass spectral library, right? And these mass spectral libraries are maintained by organizations such as the National Institute of Standards and Technology, NIST. Right, and so the idea here is that if you look up this query spectrum in this library, whatever molecule, whatever spectrum you find that is the closest match for this spectrum, that spectrum which is linked to this molecule will give you the identity of the molecule. But you'll run into a problem if the compound isn't in the library, right? Like if we didn't have, for some reason, toluene in the library, then there would be no good match for this spectrum in this library, and therefore we would not be able to identify what the compound is. So this work that I'm presenting is about trying to expand the library to cover molecules that we don't already have in it. Right, so the idea is that for whatever compounds that are missing from the library, we can generate, using machine learning, the spectra for these molecules and add them to the library. So now with this supplemented library, we have increased the coverage of compounds that it knows about, and then we can look up these compounds. So, right, the task setup then is, basically you would take these query spectrum, look it up in this augmented combined library, and then look for the top matches. And maybe the top match will be a compound that is in our predicted set. Indeed, for the way that we train and evaluate the model, which I'll get into later, we actually select query spectrum that have its true match only from the predicted spectrum. And therefore, we would hope to see that our predicted spectra is one of the higher matches, since that is the correct match for the query spectrum. So this idea of expanding mass spectral libraries by predicting the spectra is not a new one. Was there okay. It's not a new one. There's actually been a lot of models, so people have developed chemical models or physical models of the fragmentation activity using quantum mechanics or molecular dynamics. The runtime of these models can take up to hours or even days per molecule. As you can imagine, some of these calculations are expensive, and the larger your molecule, the more expensive the calculation is. People have tried to speed up this approach using machine learning prediction of the fragmentation behavior. This is work that the Wishart Lab has done. And in this case, you can definitely speed up the process by quite a bit. You can get it down to 5 minutes per molecule, but it's still maybe not fast enough if you have lots and lots of molecules you want to try out. So what this work is then is about the end-to-end prediction of mass spectra. What we want to do is we want to go directly to predict the spectra without necessarily thinking about the fragmentation steps, because we think that the model can just learn what are the peaks without learning about the fragmentation rules explicitly. It can figure out the patterns between the molecule and the spectra. So the molecular features that we use here are what's known as circular fingerprints. You can think of this representation as recording the local structure within the molecule, right? So this ethyl group might be encoded into this bit. So like this bit represents that this molecule has an ethyl group, this bit represents that this molecule has a benzene ring, and so on. Basically, this representation will encode local chemical features within the molecule. We then pass it into a neural network or a multi-layer perceptron. And then we generate a prediction of the mass spectrum. So the way that we consider the prediction task here is that we are trying to predict the intensity at every peak from 0 to the maximum mass to charge frequency or mass to charge ratio that we're going to consider, which in this case is 1,000. And then we just, for each of these bins from 1 all the way to 1,000, we want to predict the number. So like this number here represents what we think the peak intensity, what the model thinks the peak intensity should be at the number. And we do this for every single mass to charge ratio bin. So as you might note, this only really works for electron ionization mass spectrometry, since we aren't going to consider the decimal values. We're only going to consider integer values. Right, and so then how does the evaluation of the model work? As I mentioned, we will construct a combined library using partly the observed library and partly the predicted library. But our query spectrum will always have the correct match in the predicted library, right? So the query spectrum will be drawn from a part of the NIST library that's known as the replicates library. So they won't be an exact match to the original main library from NIST. And then for all of the molecules in our query set or our target set, we will remove the corresponding spectra from the original library and instead use our model, which I call MEMS, to predict the spectra. And so this makes up our combined library. Now the task then is to see whether or not the correct spectrum, whether or not when we do this matching lookup using a similarity function, the same similarity functions that are used currently by the mass spectrometry software, or right, for identifying a match, we will then look up this query spectrum in this combined library and see whether or not the correct spectrum, so that is the molecule that we expect to have the closest matching spectrum because we generated from, because we know what the correct answer is, shows up in the top 10 molecules, or the top 10 spectra. So basically, we'll look at the top 10. If the correct matching molecule for the predicted library, from the combined library is in this spectrum, we consider that a win. So this is what's known as the recall at 10 evaluation. So here is the performance of the model. If we look at the NIST reference library, so if we did not replace these spectra with our predicted spectra and only looked at the original NIST library, we end up with a performance of 98.3%. And the reason why this isn't 100% is because the query spectrum come from this replicates library, and the replicates library of spectra actually have a little bit more noise to them. So it's not a direct match from the replicates library spectra that we're using as queries to the main library spectra anyway. And so that noise is enough to make this number not be 100%. If we use the model as I described it on the previous slide, so using this multi-layer perceptron, using forward, I'll explain what forward means in a minute here, we get a performance of 50%. All right, this is clearly not high enough. There's something wrong with the model. We think we can do better. Okay, so let me show you an example of the spectra that's predicted by the model. So the spectrum for pentachloropentane. And the bottom here is what our model predicted as the spectrum for pentachloropentane. So it's really running into trouble in the higher mass to charge ratio domains. It's not getting this right. And it turns out the reason for this is because the model is not good at accounting for neutral losses. I will go over what a neutral loss means. So for example, let me take, for example, the molecule acetone. Here's the spectra of acetone, right? And then as you know, there will be an M plus peak at 58, since that's the molecular mass of acetone. If we observe the fragmentation resulting in a methyl ion, we'll expect to see a peak at 15. If we observe the neutral loss of a methyl radical instead, we end up with a peak at 58, the molecular weight minus 15, which is 43, so which you'll see right here. Okay, what happens if I look at butanone instead, right? One extra carbon. The same thing, right? We expect the F plus peak at 72. We expect the methyl fragmentation of an ion, so then you would expect to see a peak at 15. And if we consider the neutral loss of the methyl group instead, you end up with a peak at 72 minus 15, which is 57. Right, so there's this pattern here that there should always be a peak at not just the weight of this fragment, but also a peak at the fragment that's located at the molecular mass minus the small fragment that's being removed or being ionized. Now, the thing about the fingerprint representation that I showed you before is that it's really not designed to handle large groups, right? So here's an example from this review paper that is useful if you're interested in reading about generative models in machine learning. But basically, this shows you that this representation is only really good at capturing small groups in the molecule, right? You can only really see that there's a sulfur group or there's a benzene group and so on. It's not very good at capturing the bulk structure of the molecule. So in other words, that original structure here, this is a relatively small example. So in this case, the model probably could capture it. But if you imagine that I had an ionization event on this molecule instead, it's not going to be able to capture the structure of a large fragment of the molecule, right? It can only see the small fragments. So how do we account for this then? So rather than only predicting the peaks at each bin, so starting with charge to mass, only considering the charge to mass ratios in a forward direction, right? So like, as I mentioned before, the goal was to predict the intensity at each bin, and each bin represents a specific mass to charge ratio. We'll now give the model a little bit of extra information, which is it will know the molecular mass of the molecule. And then when it knows the molecular mass of the molecule, we'll actually have the models make predictions of peaks that are located whatever distance away from the molecular mass of the molecule, right? So like, for example, if we wanted to model the methyl removing behavior, we would expect to see a peak at the molecular mass minus 15. And so in this way, we basically gave the model a little bit of help. We inserted a little bit of prior knowledge about neutral losses, about mass spectrometry into the model. And so we call this, in the paper, we call this the bidirectional spectrum prediction method, right? Because it's starting from the molecular mass of the molecular mass of the molecule and then subtracting out the neutral loss of a small fragment. Okay, so this is the prediction of the spectrum of pentachlorobenzene, as I showed you before, with the old model, and here it is with the new model that uses bidirectional prediction on the right. And so you see now on the right, if you look at the higher mass to charge ratios, we're actually doing a lot better, right? You can see that now at least the larger peaks are being matched up pretty accurately. So, right, this was the performance of the model before. This was the performance of the reference NIST library. Here's the performance of the forward model. So that doesn't use the bidirectional prediction. Here's the performance of the model using bidirectional prediction. So we have a huge increase of 30%. To get the final model, we actually also apply what's a mass filter. So basically, from the reference library, we filter out anything that doesn't have the same molecular mass, or we only include in our library search those molecules that have a mass of plus or minus 5 of the molecular mass of the molecule. And in this way, we can get to an accuracy of 91.7%. And I should mention that the main motivation for us to have this algorithm is because we wanted to make predictions really quickly, right? So now this model can make predictions for a single molecule in 0.47 milliseconds, compared to 5 minutes from the previous machine learning model. Since this work was published in 2019, there's actually been a lot of work in this space. For example, there's been some work in directly predicting the molecular fingerprint from the spectra, so from the electron ionization mass spectra of the molecule. There's also been work in using better models or different architectures for predicting the spectra. So this is a really active area of development. Okay, so now let me transition into the second part of my talk. So the first part of my talk, right, was talking about teaching machines to recognize chemical signals from devices, or to mimic or to predict the chemical signals that it's getting from mass spectrometry. Now, this part of the talk will be a little bit more general, which is we're going to think about modeling the human perception of molecules of scent, right? So rather than thinking about the representation as according to a machine, we're thinking about the representation as according to humans. So our goal is to digitize scent. And as you know, when you smell a rose or you smell tea, you're not just smelling one molecule in actuality, you're actually smelling a mixture of molecules, right? There are multiple compounds that are responsible for giving you the smell of a tea. But we wanted to break this problem down into the simplest possible version of the problem, which is to consider the scent of the molecule, one molecule at a time, right? So here is a vanilla plant down here, and in this case, we're just going to focus on the molecule vanillin, even though the vanilla plant might produce many other compounds which are responsible for the smell of vanilla. So the data set that I'll be showing you in a minute is going to be a data set that's compiled by expert perfumists, right? So an expert perfumist might smell a molecule like vanilla, and they're trained for many, many years to learn various odor descriptors, right? So here's a selection of some of the odor descriptors that they might learn. And they spend a lot of time training their noses so that they can accurately pick out the individual notes, or they can smell something and then come up with an accurate description of the smell, right? So for example, vanillin here might have a description like it smells sweet with a hint of vanilla, some notes of creamy, and a back note of chocolate, right? So in this case for vanilla, the odor descriptors that we assign to this are sweet, vanilla, creamy, and chocolate. Now, I should mention that this problem is highly, highly nonlinear, right? So if you're familiar with problems in drug discovery, right, there's this notion of an activity cliff, where you make a small change to the molecule structure and you end up with a dramatic change in the activity of the molecule. The same thing that happens with olfaction. So here is an example of Lyrol. This is responsible for the smell of like dryer sheets. It smells like lily, and so it has these odor descriptors: gay, which is another word for lily, fresh, floral, sweet. Making some small changes to the molecule structure doesn't result in a large change in the odor structure, right? Like, so this change here, where you just shorten the carbon chain, has mostly the same smell. This change here, where you replace this group with a mostly similar group, also doesn't have a change in the smell, in the perception of this molecule. Making a change like this one, which is a relatively large change, right? Like it basically breaks this ring open, ends up with the same smell anyway. Whereas if you look at this molecule here, where we shifted double bond around the ring, this change is considered significant enough that now we have an odorless molecule. So this is a dramatic shift in activity. So this is by no means a easy problem to solve when we're trying to think of the patterns that we look for in the molecule to try to predict its scent. All right, so now let me tell you about this data set that we constructed, right? So this data set has approximately, that we finally used, it has approximately 5,000 compounds. It's a combination of these two perfumery data sets. Here's that molecule vanillin that I was showing you earlier, right? So this molecule vanillin has 4 label descriptors. So like this first histogram up here shows you the distribution of number of labels for each molecule. And so you can see that many molecules have roughly 4 labels. Some of them have fewer. Some of them even have as many as like 16 in some cases. And that's partly because some molecules are more complex and have a combination of odors. It also could be because when people smell different molecules, occasionally there are some molecules that might trigger a wide variety of responses or a wide variety of smells for different people. And so as a result, when you combine the labels, you end up with 16 of them in some cases. But this is by far an outlier. And for the most part, you'll have molecules between like 2 to 5 labels, roughly speaking. If we instead look at this figure B down here, and think about the number of molecules we have for each label, you'll notice that we have some labels with lots and lots of molecules, right? So for example, the label fruity has over 1,800 molecules. The label sweet and green have roughly 1,400 molecules. And these labels, fruity, green, sweet, and floral, are considered superclasses of odors. So within floral, you might have labels like jasmine, lily or bouquet, rose, and so on. So basically, these labels are considered superfamilies of odors. You also have some other odors like solvent, orange flower. These odors don't occur as often and show up at the tail end of our distribution. And actually, for those odors that don't occur frequently enough in our data set, we actually just remove the label from the data set. And I should note that because this data set is compiled from a perfumery data set, this data set is heavily skewed towards pleasant smells, right? So we don't have many unpleasant smells like sweaty or wet sock or something like this. I want to show you one more figure on the right here, which is this figure C. And here you can see this is a co-occurrence matrix of all the odor labels, of the 137 odor labels we look at in this data set. And what I mean by co-occurrence is that, for example, in vanillin, we see that sweet and vanilla co-occur, are present, both odor descriptors that are present in the same molecule. And so it basically counts this graph is a count of the frequency that 2 odor labels will occur in the same molecule. Right, and so you can see that this space is highly structured. You can see little clusters of odors that are frequently present in the same molecule. So for example, for toasted, baked, you can see that these odors include cocoa, coffee, and popcorn. These odors here have alcohol. In alcohol have rum and cognac and malt, and fresh fruit down here has apple and pineapple, and so on. So this space is highly, highly structured. All right, so I don't want to spend too much time going over the model that we used. I think I see that I'm kind of running short on time, but so in general, we use the graph neural network model. The graph neural network model is very well suited for problems that have graph-like structures, which in this case, a molecule is, if you think of the atoms as nodes in the graph and the bonds between them as edges. If you want to learn more about graph neural networks, you can learn more at this blog post that my teammate Ben Sanchez made at this link here. But the main key things that I want you to take away from this figure is that this graph neural network model allows us to learn a specific odor representation for the molecule. And the task here is to, given a molecule, we want to predict which odor descriptors this molecule has, right? So this is vanillin again. We want the model to be able to predict that it has the odor labels vanilla, creamy, sweet, and chocolate. And we'll do this for every molecule in the data set. So here's the performance of the model. Our model's performance is represented on the y-axis, and the best prior method or the best prior model is performance is on the x-axis. And so the model before was using a simplified model. This is basically a decision tree using the fingerprints representation. And this is our model on the y-axis. And you can see that each circle here represents a different odor label. And most of these dots, these odor labels, end up above the y equals x line, indicating that our model has better performance than the previous method. We're interested not just in the performance of the model, but as I mentioned, we're also interested in learning a representation of odor. So with this model, we actually have a chance to look at the representation that it's learned by looking at what we call the penultimate or last layer of the model right before it's making these predictions, right? This is sort of supposed to be a distillation of everything the model has learned about odor. This is the customized representation for odor learned by the model. And what happens when we look at this space? Right, so I'm going to show you principal components analysis, or PCA, of that 63-dimensional embedding space from the last layer of the model. And you can see that actually in this space, different odor groups are tightly clustered together, right? So here's all the musks clustered in this part of the embedding space. Here's lily clustered on the left-hand side of the graph. And now you can see grape is clustered at the bottom. And finally, you can see cabbage clustered at the right. And you can roughly think about it as the pleasant smells are more on the left-hand side of the graph, and the unpleasant smells are more on the right-hand side of the graph. If I now look at the super families of odors that I described earlier, like floral, so here's muguet, which is lily, lavender, and jasmine. They all co-occur inside of the big floral cluster, right? You can see that they're all located roughly inside of the big shaded green cluster. I can do the same thing if I look at meaty. So here's meaty and a bunch of words that are related to meaty, also co-occurring inside of this structure. And here's alcoholic, where cognac, fermented, and winey are all co-occurring inside of this this alcoholus shake, which is conveniently shaped like a wine bottle. To show that this representation is useful more than just for our data set, we actually applied an approach called transfer learning. So that is to say, we took the representation learned by our model and then used it for other tasks that were, while related, they're still human olfaction tasks, have a completely different setup. So the Dream Olfactory Challenge actually is a data set where human raters were asked to rate the molecules on a scale, rate the molecules for each of these 19 odor descriptors on a scale of 0 to 100. So this is now a regression task. Also, the human raters used for this experiment were not expert perfumers. They were just people who were trained briefly to learn how to smell things. And then they came up with these ratings. So there's a lot more noise in this data set. And yet, again, we have our models, or the model based on our representation that I described before on the y-axis and the previous model on the x-axis. And you can see that the model that's using our representation is doing better. We can see this again for this other data set, Dropnieks, which uses more word associations to make the predictions. And again, we see that this embedding is actually useful for this representation. So we really think that the representation that we've learned from this model is a generalized representation of odor, of human perception. Now, we're not sure if this will be like the final representation of odor, or if we can this will truly become the next RGB, but we think that this is a step in the right direction, and a step towards finding the correct representation of odor. So in this talk, I've described to you two approaches, or two projects that I see as the really early stages of coming up with a way to digitize chemical sensing. I talked to you about expanding mass spectral libraries using machine learning predictions, and in general, trying to use machine learning to predict and estimate the outputs of electronic systems for detecting chemical sources. And I've also talked to you about a way of coming up with representations for the human olfactory experience. And I think these two projects sort of represents initial steps towards the final goal of digitized chemical sensing. With that, I'd like to thank my teammates and collaborators. For the mass spectral project, I'd especially like to call out Dr. Steven Stein at NIST. Thanks to his help, he was able to provide us the format of the data set that we could use for machine learning, and also gave us a lot of initial advice about the project. And I'd also like to thank Dr. Laura Castellanos at the University of Massachusetts Amherst, who also advised us at the beginning stages and gave us edits on the final version of the paper. And with that, I'd like to thank you for your attention, and thanks once again to Chulomko for having me today. It was my pleasure to speak, and I'm happy to take your questions.